Preparedness. So, boy, 2 years ago, no. How long ago was it, honey? July of 2009. My wife and I get back from a wonderful family barbecue and both realized we absolutely would not survive a survival situation. All I could add was that I had a lot of toothpaste in the closet. All she could add was that she knew it was important to use toothpaste. And over the years, we have, we think about some of these things because society is pretty much dependent on the internet, electricity, water, etc. And I actually got into ham radio, both because I'd always wanted to, but the real motivator was I want to be able to communicate no matter what. And over time, that led me to figuring out, well, I've got a generator, yeah, but gas runs out. So what are my other alternatives? What's renewable? What can I do? And that led me into this unholy quest to get into portable solar power. So what I'm going to talk to you about today is basically how to run a portable station, disconnected from the grid, the things you need to think about when sizing a system, considerations, talk a lot about battery technology. What I would ask is that if you have a question as I go along, please ask it. If you see something that is just completely wrong, call me out on it. This will only get better if I get feedback. And I'm not an expert. I'm not an EE. I'm just a guy who's determined and loves surfing the internet. And that's where the majority of my knowledge comes from. So there's also some swags in here. And if you ask a question I don't know the answer, I'll either make up a good one or say I don't know. All right, so I'm going to cover in this presentation figuring out what the needs are as a portable radio operator, talk about the components of a base system and some accessories that make your life a lot easier, and then we'll have an official question period at the end. On the screen, there are two solar setups. The one on the left, the one on your left is actually one that a friend of mine in Wisconsin just built. He's not a radio operator, but he wanted to be able to charge cell phones and a couple other accessories portably. The one on the right is a setup that I built, with the exception of the panels, from scratch that mirrors very much like the system I had at Field Day. So the first thing that we need to do is figure out what are my needs as a portable radio operator. What kind of equipment am I going to be using out in the field? I need to understand what are the power requirements of the radio that I have, and am I going to be bringing a laptop, lighting, an iPad charger, a phone charger? I need to understand what I'm going to be trying to use in the field. Then I have to figure out how long do I want to be able to operate. Do I want to operate a 100-watt radio for 24 hours, constantly calling CQ, or do I just want to be able to do QRP for a few hours? So starting off with the common rig that most HF operators have, this mobile 100-watt class of small portable radio, 13.8 volts, plus or minus 15%, voltage requirement 11.7 to 15.8. I'm going to say a lot of these number things. This will be important later for battery stuff. I don't go into this necessarily in the depth that it deserves because math puts people to sleep, but this is something to be mindful of. On average, this classification of radio draws 1 amp of current on receive. If you're doing CW or any other continuous mode at full 100-watt power, on average you're talking about 22 amps. Sideband, you're anywhere from 12 to 18, depending on how much you're modulating, how much compression, etc. And a very important thing to remember, radios are terribly inefficient. By definition, their job in life is to heat up the atmosphere. I say radios are less than 50%, but it's really closer to about 33%. A common requirement for emergency communications and basically supporting the community are these mobile VHF, UHF 50-watt rigs we all have in our vehicles or at home in our base stations. Same voltage requirements, 13.8 plus or minus 15%. 1 to 2 amps draw on receive, up to 16 amps current draw on a full 50-watt power output. Again, well under 50% efficient. The last thing I cover, QRP radios, because some of us just like to throw a radio in a backpack, go walk somewhere, and stick a wire in a tree and go for it. So the two most popular right now, the 817, quarter to a third of an amp on receive, 2 amps, transmit up to 5 watts for continuous carrier, and 1 to 2 amps on sideband. The new Elecraft the KX3, 8 to 15 volts, 150 to 200 milliamp on receive, up to 3 amps at 10 watts for a continuous mode, and 1 to 2 amps for sideband at 10 watts. Okay, so we've talked about radios. Let's talk about the components of a portable operating system. This is a setup that I have from my earlier days of experimenting. I've got everybody's got one of these 7 amp hour, 9 amp hour AGM batteries. They say 9, they're only 7, trust me. The little neon green box is a solar charge controller, which is what is actually interfacing between a panel array and the battery. I got a couple of solar panels. In this, I also have a meter measuring the performance of the solar panel. Now, one thing you might notice, it's completely cloudy. That's a 30-watt panel array, and I can't tell, I don't know if you can see this, but I'm still getting almost half an amp out of it, and 5.4 watts, so 1/6 efficiency under completely clouded over skies late in the afternoon. The reason that I'm here today is because everybody loved my field day station. For field day, for those of you who weren't there, completely solar and battery. The laptop, the radio, our lighting, the candle, no wait, that's not right. Everything completely off a portable power setup. Now, what I was using is a commercial product by a company called Goal Zero. 100 amp hour battery, built-in charge controller, built-in pure sine wave 120 volt inverter, USB ports, native Anderson power poles, as well as a cigarette lighter socket, and then I had a 120 watt solar panel array. So again, at this point we've covered 3 basic components. You need a battery, you need a charge controller to charge the battery, and you need your solar or photovoltaic cells. Again, at this point we're assuming everything we're doing is a 12 volt system. Solar goes up 12, 24, 36, 48 on up, and there are reasons to do that when you're talking about home systems or if you're working with long runs of cabling between your panel. But again, since we're hams, like to keep it simple and on the cheaper side, strictly 12 volts. Your system may include other accessories like inverters, so you can have an AC power source, metering, boost regulators, etc. Batteries, the starting point, because battery is really the thing that you are going to pick, whose size will really determine how you're going to be able to operate, how long you're going to be able to operate, what you're going to be able to do to operate. Battery selection also will determine how much solar power, how many watts of a panel array you're going to want to have in the end. And again, this is where we first start considering what is the current draw on my radio, how long do I want to operate. So we say, what kind of batteries do I need? Batteries are rated in amp hours. Who here knows what an amp is in true scientific terms? Rick, you should know this.
I should, but I've forgotten the numbers.
So an amp is actually a measurement of a rate. Did you know that?
It's so many coulombs per second. Right?
That's right. How many? 3,600. So no, that's exactly right. Because this rating, it's not amps per hour, it's amp hours. If you do stoichiometry and do the units, it all works out. The thing is, no matter what kind of battery you pick up, the amp hour rating is dependent on how long it took them to discharge it. Standard lead acid or lithium pack you pick up, the amp hour rating you're going to see is based on a 20-hour discharge. And during this period, this rating is based on killing the battery, 0 volts. And hopefully most of you know that any battery technology that we're not talking about double L, A, or dry cells, 0 volts is dead. Dead. You're not really going to resurrect it dead. As an example, a 20 amp hour battery rated for a 20-hour discharge means that that battery took 20 hours to discharge at a 1 amp rate. Also, as the discharge rate on a battery increases, the overall capacity of energy decreases, and that's called the Pukert effect. This is a formula that I sat out and I was like, man, how can I quantify this in math? Because it is a little bit difficult. And I got this, I got the idea from this from another ham up in Maryland. who I put a link to his site at the end of this thing. Basically, when calculating amp hours, I think it's a lot easier to say, what's my average hour of operation going to be? So here I have, the received percentage, R%H, is what percentage of an hour am I going to be receiving? So for example, 75%. And I leave it as percentages so we don't have to convert between minutes and et cetera. Times received current. And then plus time, or the percent of the hour I'm going to spend transmitting, say 25%. Times transmit current, times total hours of operation equals my estimated capacity. And to make this a little easier to understand, let's say we want to operate an Elecraft KX3 on sideband full power for 8 hours. We assume that in an average hour we will spend 25% of the time talking, 75% of the time receiving. Per our earlier figures, I've got a quarter of an hour times 2 amp, which was our transmit peak current, plus 0.75 hours, 75% of an hour, at 0.2 of an amp, equals 0.65 amp hours to support 1 hour of estimated communication. Multiply that by 8 hours, I come up with 5.2. These numbers I don't expect you to remember. Go back, look at the formula, but this just shows you what our starting point is. This formula is also not incredibly accurate. This is really just designed to estimate for you a baseline. Any questions?
So when you want to do an overage, actually, like twice that, you wanted to say?
Well, you do, but there are actually provable reasons why you want to. First of all, you're not going to find a 5.2 amp hour battery.
Right.
So the common size, if you go lead acid, is a 7 amp hour battery. But as we cover battery chemistries, you'll find out why you actually have to. Because again, that 7 amp hour battery is not a 7 amp hour battery. So just remember that in our example, we were talking approximately 5.2 amp hours to do what we wanted to do. Operate sideband out in the field, 8 hours. We're going to focus on baseline or chemistries. There are going to be 2 chemistries that a ham will consider. I'm ignoring AA's. I'm ignoring rechargeable, any type of nickel metal hydride, nickel cadmium, alkaline. We're not talking about that scale because most of us aren't running our radios off those things. If you do, there are plenty of sub $100 products you can buy to keep 4 AA's charged in the field. So you're primarily going to look at either lithium chemistry, lithium ion, lithium polymer, lithium iron phosphate, lead acid, and for that, hams will look at a flooded deep cycle marine battery, an absorbed glass mat battery, or a gel cell. Who's familiar with golden triangles? Anybody any project managers in here? So, golden triangle tells us that there are 3 factors in a system. You can have 2 at the expense of the third. And in this particular instance, batteries fit this model perfectly. Portability, energy capacity, cost. I can have a battery that maximizes portability, energy capacity. The cost is going to be great. I can optimize to have a battery that is portable and low cost, but the energy capacity is going to be reduced. Or I can optimize for energy, maximum energy, lowest cost, but the portability is going to be really down. Does that make sense? Okay. Just looking at some high-level factors of battery chemistry. Lithium versus sealed lead acid. Lithium batteries are going to be light. Sealed lead acid are heavy. That has something to do with that lead in the name. Cost, lithium batteries are expensive, whereas sealed lead acid, they're affordable. Size for the lithium is a very energy-dense technology, so the batteries tend to be smaller. You all know sealed lead acid batteries are quite large. Safety, lithium batteries, lithium ion, lithium polymer, could be fire risks. Dover discharge them, puncture them, expose them to air, they could be fire risks. Lithium iron phosphate are safe though. Sealed lead acid, relatively safe. Availability, for the types of packs that we need, there's a Batteries Plus across the parking lot from Atlantis. You all can go buy AGM batteries. The lithium packs we need generally are going to require being ordered. So, starting with sealed lead acid, because this is the most common battery a ham's going to have. Absorbed glass mat or gel cell. 2 different technologies to create a sealed lead acid battery that is, well, sealed. And does anybody know why a sealed lead acid battery is important. What does it not do that a traditional flooded battery does?
Yeah.
That's right, it doesn't vent. This is important because, well, you don't want to spill acid on yourself, you don't want to blow up. So you choose these batteries for safety. They're a little more expensive, but they are inherently deep discharge. Avoid flooded batteries. You can go to Costco and for $60 buy a 200 amp hour marine deep cycle battery. It weighs 130 pounds, and if you tip it, it spills acid all over the place. It vents a lot of hydrogen, and you're going to need a high charge current to keep that thing charged. Don't fool with it. For portable operations, you want safety, go with this. Car, lawn, power sports flooded batteries, they're not designed for deep discharge. They're designed to provide a lot of current in a very short amount of time. So they really start getting iffy if you discharge them more than 80%. Sealed lead acid batteries, if you leave them off of a charger over time, they will slowly lose current, and I'm sorry I don't have a rate of loss, but I mean after 6 months, you lose about half of your energy of a battery sitting around. You guys have experienced this in cars that we let sit for a while. All right, on the left-hand side, I've got basically a linear, it's a discharge curve, if you will, of a sealed lead acid battery. Nominal voltage of a fully charged battery, 12.8 volts. The minute I put even so much as a tenth of an amp on there, that immediately drops to about 12.5. You'll notice from 100 down to 40, I'm losing, except for the first jump, I'm losing about a tenth of a volt per percentage. You'll notice that's the green zone. Generally speaking, this is the area you want to be operating a sealed lead acid battery in. Notice in the yellow zone, we get down to 11.8, and our voltage starts dropping twice as fast per percentage. Remember, our radios can in theory operate down to 11.7, but you're starting to fluctuate with discharging this far will shorten the number of total charge and discharge cycles you'll have with a sealed lead acid battery. The red zone, you're flirting with killing the thing. And killing is kind of, what's that?
There's no parking in the red zone.
No. I mean, on average, you're going to have, 200 to 500 recharge cycles for a sealed lead acid battery that you don't go below the 40% depth of charge. Yes, you can discharge a battery to 10.5 or a little bit below that, but you may have literally cut its number of discharge and recharge cycles to anywhere from like 5 to 50. So, I mean, that takes a toll. Let's see. So, when not in use, something else too, and I'll cover this in a little bit more depth. These batteries should be kept on a battery maintainer like a battery tender, etc. These things are plentifully available online and through local retailers. So, the previous slide tells us our radios will only operate down to approximately 30% charge of the battery. So this means when you purchase a sealed lead acid battery, going back to Marshall's point earlier about overshooting, if that battery says 20 amp hours, that's actually not quite true. You're only getting 14 amp hours of usable power out of it, because the rest of it you're getting into, again, the danger zone. Also, some radios are finicky about voltages below 12.5. The ICOM IC7000 does not operate at full power within that 15% band on either side. So, going back to the example earlier where we said we wanted a 5.2 amp hours of operating energy, here's a formula. Our requirement to fulfill our 8 hours of operational, I've got 70% times the amp hours that I need, gives me 8 amp hours total for the battery. So sizing wise, I'm either going to compromise a little bit and get a 7 amp hour battery, or I'll move up to like a 10 or 12 or whatever the next size up is. Does that make sense to everybody? The takeaway from this is you buy a sealed lead acid battery, you're only getting 60 to 70% of the energy it advertises to have. Moving over to lithium, primarily we're going to talk about well actually, are there any questions about sealed lead acid batteries? No? Okay. On the lithium side, we're going to talk about lithium ion, lithium polymer, lithium iron phosphate. There's also like 75 other lithium ion technologies that are specific chemistries. Maybe it exists only in a university lab. Maybe they're made for a specific classification of medical equipment. But the batteries you'll see that you're looking for consumer will say lithium ion, lithium polymer, etc. Each of the lithium technologies do have slightly different characteristics, which I'll cover here in a moment. Does everybody know that battery actually means a collection of cells? Sometimes we think of a AA battery. It's not actually a AA battery, it's a AA cell. Lithium are always going to be packs of cells, usually shrunk wrapped together, etc. In the case of ham radio stuff, being in the 12-volt world, you'll usually see 4, and you'll see why in a moment. Another thing that's important is, let's see, lithium packs, because they have such narrow voltage ranges for operation, etc., you have to do something called balancing. In a 4-cell pack, there are specific charge controllers out there that actually make sure each cell in the pack is exactly the same voltage. This is similar to the idea, I always see the warning on your remote controls, right? Don't mix old and new batteries, because then your total battery pack together becomes as strong as the weakest link in the chain. And because of some of the things that lithium does, if you get a cell in your battery that gets really low voltage and resistance ramps up, and obviously all kinds of bad things can happen. But yeah, you do that with a balancer, or either a balanced charger or a balancing cell. Lithium-based batteries have much higher energy density compared to SLA. Again, a 7 amp hour AGM battery that we're all familiar with weighs like what? I don't know, 7, 8 pounds? I'm not good with estimating weights. I should have added this. Similarly, I can build a lithium pack with the same energy density that weighs a pound. And it's going to be smaller. Lithium batteries have a flat discharge curve. So what this means is, when you hit the 3 volts per cell, that voltage will stay right there until you get to the 90% mark of the battery. Earlier I showed you how the voltage dropped as you discharge a lead acid battery. That doesn't happen with lithium batteries. Lithium batteries are very sensitive to being overcharged. They require a whole lot more care and feeding than a sealed lead acid does. In other words, they're not as tolerant to abuse. We talked about the balancing. Going into our different types of lithium chemistries, lithium ion, lithium polymer, same characteristics. I don't know why I actually didn't just put them in one column. But lithium iron phosphate is a relatively new technology. Comparatively, it's been around for about, I think, 8 years, something like that. The primary company that is out there making these things is a company called A123. There are Chinese knockoffs, but A123 cells are found in the Prius and almost all of the different hybrid vehicles that are out there. They only come in 2 sizes. An 18650, which if some of you have lithium rechargeable flashlights that use CR123s, you're familiar with that. It's the size of 2 CR123s. And a 26650, which is about the size of a C cell. You have cars out there that are running on packs that may have 100 of these batteries in them. And that's actually one thing that is pretty impressive about them, is the technology is so foolproof you can build packs that big. Try doing that with nickel metal hydride AA's. It won't work. You really run into high failure rates when you get to more than about 11 batteries, 12 batteries in a pack. Nominal voltage is your operating voltage. So lithium iron phosphate 3.3 versus 3.6 to 3.7 with lithium ion and lithium polymer. Peak voltage, meaning this is when the battery signals that it's charged, is 3.6 volts versus 4.1 for the other 2 lithiums. Minimum voltage, meaning this is the line you do not cross. 2 voltage for LiPo, LiFePO, 3 volts for the other 2. A nice thing about the lithium iron phosphate batteries is they're good for 1,000 to 2,000 cycles. If kept in the constraints. Whereas the other lithium technologies are in the low hundreds, the 1 to 400 range. Voltage under load, 3 volts versus 3.3. Max discharge C. C is a current rating, but what it specifically means is times the amp hour rating of the battery. So in the case of lithium iron phosphate, a small cell can be discharged. If it's a 2.6 amp hour cell, you can discharge it at 30 to 60 times that rate of current. Now granted, at those rates, the battery's gone like that, but it can withstand it. It has an incredibly low internal resistance. Traditional lithium technologies is only about 20C. For radio stuff, we don't care. We're not approaching those limits. If you're building an electric vehicle, an electric motorcycle, a scooter, you care about that. Torque equals current. I mentioned to you about the balancing. Lithium iron phosphate batteries have an infrequent requirement for balancing, which is important because I can charge them with a solar charger out in the field, don't have to worry about balancing them, then balance them when I get home. The other lithium cells, you can charge them without a balancer, but you really shouldn't. So in case you can't tell, I'm really trying to make a case here for lithium iron phosphate. You'll see these packs listed as 4S integer P. What that means is 4 cells in series times X number of cells in parallel. So for instance, if I had 4 2.6 amp hour A123 cells, 4 series 1P would mean that the whole pack is 14.4 volts at 2.6 amp hours. The lithium iron phosphate batteries are slightly heavier than the other lithium technologies, but the benefits really outweigh it. Most importantly, I can microwave a lithium iron phosphate battery, I can put a screwdriver through it, I can set it on fire, I can hit it with an incendiary round, and it will not catch on fire. It will not burn me, it will not heat up, it will not catastrophically fail. Lithium polymer batteries can catastrophically fail. People have had iPods go up in flames in their pockets. The technology is a little safer today, but that's another reason I just don't want to fool with them, and I don't recommend you do either, even though they are a little bit cheaper. Any questions on lithium battery technology? Was what I'm saying make sense? Again, nodding heads because you're asleep or because you're understanding. All right. Next we'll move into charge controllers. Again, the charge controller is the thing that couples a set of solar panels to charge my battery. The thing is there some advanced science going on here with these in some ways? Because the question I get is, well, if I have a charge controller plugged into my battery and I've got a radio plugged into my battery and I'm drawing current from my battery using my radio while it's being charged by the sun, what's the solar panel doing to my radio? I have no idea. I have not figured this out. In theory, yes, their battery at that point is just acting as a capacitor, but nobody's explained to me the science behind it to talk about that. Let's see. Some solar charge controllers, like the one you'll see on the left is the buddy pole one. It's a series device. Panel, charge controller, battery. If you want to run your radio, you're connecting your radio directly to the battery. The other three all have load circuits built into the charge controller. So, panel, charge controller to battery, separate leads to your load. Other optional features are low voltage disconnects, so it won't let you run a battery down to a failing point. It may have metering built into it to show you the health of your batteries, the current coming in from your panels, the output power. Switching, meaning that you can hit a switch to turn your load on and off, etc. And some of them also have the feature to take 12 volts in and output 24 volts, take 24 volts in, output 12 volts, etc. But again, we're totally talking about 12 volt systems. Solar charge controllers, by and large, are mostly available for sealed lead acid batteries. Though I now know of 2 portable field solar charge controllers that work with lithium packs. And this is actually something I learned in doing this presentation. There is a company, which I'll talk about a little bit later, called Genasun, which they are, to my knowledge, the only company that makes small portable solar charge controllers for lithium chemistries, which is pretty cool. You have 3 types of charge controllers. Pulse width modulation, meaning that it uses, modulating widths of a pulse burst to charge a battery. Maximum power point tracking, which is really the most efficient style of charge controller, meaning you get the most energy from the sun into your batteries. And then cheap. And the reason I put cheap is because some charge controllers are nothing more than a diode, a resistor, and a heatsink. Other charge controllers use really old bucking circuits to do voltage step up, and all they'll do is absolutely just slam your battery with a constant voltage, and you hope it balances out when it gets full. So obviously we recommend to stay away from anything in that category. Good charge controllers make it impossible to overcharge a battery and charge using multiple, and they also charge using multiple stages. In battery terminology for sealed lead acid, there are actually 3 stages of charge. If the battery is nearly dead, there's bulk charge, which is get the energy level up fast. Absorption, which covers usually the last 20% of your state of charge, but it also uses a higher current mode to help desulfate battery plates inside the battery, which is important, but I haven't really gone into. And then finally, what you guys know as a trickle or a float charge to make sure your battery stays charged. With, I don't know, maybe I didn't cover this. For lithium batteries, you really only have the bulk and float components of that. Charge controllers come in various power and current ratings. So pulse width modulation charge controllers, these are going to be devices that cost between $30 and $100, depending on what features you get, how high power it is, what voltages it does. This is the modern mode of charging batteries. Again, pulse width modulation limits sulfating that occurs with traditional, and this is important because it leaves the maximum surface area of the lead plates in the battery to be used for energy conversion. They have a downside though because, when you plug a solar panel into them, a solar panel has a nominal voltage between 14 and 18 volts when there's a load on it. But when you plug it into a charge controller, it brings the voltage of the solar panel down to whatever the voltage is for the charging stage. And what that means is you could be missing out on power, which I'll show you a power distribution curve here in a moment. It works fine, but it means you're not getting the maximum energy back out of your panels. The couple of recommended brands and models for these, a company called Morningstar based out of Pennsylvania. They make many charge controllers from small portable ones all the way up to, you guys have seen the road construction signs that have the solar tech panels hanging off of them, that, the panel. Those most likely have a Morningstar charge controller in them. Morningstar also makes stuff that could power facilities. I mean, this building could have they make huge, if you had like a 2 kilowatt array size stuff. A couple of models specifically to look for are the Sunsaver and the ProStar. And there's a German company called Stecca that I like. And I like them because they have a lot of integrated metering features built into the charge controller. And as you can see in my chart here, these charge controllers are available in many different currents. And that current means, so for instance, the Stecca PR10 means that it can handle 10 amps of current in for charging, 10 amps of current, from the solar panel, and then 10 amps of current out to the battery, as well as 10 amps of current running through its switching system. When I talk about pulse width modulation controllers, it's kind of a misnomer because maximum power point tracking controllers also use pulse width modulation technology on the battery recharging side. But the big deal here is it isolates electrically the solar panel input from the battery charging output. Now, is my chart visible? Okay. What you see in the yellow box is the surface area of the power curve under where, Power is voltage times current, right? Everybody remember that? I like to remember that by remembering pi. No takers? It's getting late. In this curve, what you see in the red line, the y-axis is current, the x-axis is voltage. And what this shows you is the point that's plotted on the line would be the amount of power coming out of the system. So in this chart, I think it's easy to see if you have a high voltage but a low current versus a low voltage and a high current, you would have the same power. Where it says P max though, this is where a microprocessor has actually cycled through loading the panel at different voltages and currents to actually maximize the power rating. In other words, where the voltage times current equals the highest value, thereby getting the most power out of the panel, independent of what's going on in the battery side. So the net effect of this is, I've read you can get like 15 to 30% more energy out of a given set of panels using a maximum power point charge controller than you can using just a traditional standard pulse width modulation. I have one of each. I haven't directly empirically tested this, But the science behind this makes absolute sense, because there is a microprocessor in here that literally maybe 50, 60 times a second is recalculating what is the best possible position, which is good, because if you've ever had to maintain a solar array and keep it aimed at the sun, you find out the sun moves a lot faster than you ever give it credit for. Have I made sense on this? This is probably the newest and most important part of the presentation. So does maximum PowerPoint tracking make sense? Any questions? No? Again, some recommended brands. Morningstar again. I actually own this SunSaver MPPT. I have this in my battery box that I built. Works wonderfully. The only downside is that it's only a 15 amp charge controller, because this thing is designed for you to be able to hook up to an outlet in your house. Excuse me. The switching side of it, this thing actually has an on-off switch. It would allow you to connect a load to the battery through this thing. There's an optional meter for it. It would allow you to track all of your power usage, etc., going through it. Problem is, our radios need 22 amps for a full power 100 watt radio. And this thing, it doesn't have a fuse, it just has a smart switch that when it detects overcurrent, it basically shuts off for 10 minutes and waits for the load to reduce and then turns itself back on. On the other side, this is the exciting one that I just found out about, is this company called Genasun, which they're Massachusetts is where they're based out of. They make maximum PowerPoint charge controllers that are specifically for lithium chemistry batteries. They also sell them for lead. When you order one of these things, let me go back. The one above is about $220. It has a lot of computer options that you can, if you're into logging data, there's a lot of built-in functionality there, panel meters, etc. The Genasun model for the 5 amp version sells for about $125 for the lead, $135 for the lithium. They also have a 10 amp that sells for about $170. That's actually a pretty good deal, because this thing is tiny. This thing is made for small portable installations like we would be working with. The last thing is this little guy by Buddy Pole, which they actually just released. It's either right before Dayton or at Dayton. It's tiny. It will do 75 watts. I put 5 amps, but it's actually 6.5. This thing is cool because it will charge either an AGM, sealed lead acid, or a LiFePO pack, or lithium iron phosphate, which they sell. It doesn't do balancing, just like the other chargers don't do balancing for lithium packs, but it's, again, because lithium iron phosphate is such a tolerant technology, this is fine, and look how tiny it is. It will also, I think it has a light that'll warn you if your battery or your solar cell output voltages drop below safe levels. Any question on solar charge controllers before I move on to panels?
Which one of these do you prefer, you think, at this point?
Personally, I still really like my SunSaver MPPT. But that's because, for me, part of the enjoyment I get out of building these things is I love data logging. And it makes it like, I can connect that thing to an Ethernet network. There's their bridge available. I have an RS-232 interface to hook it directly to a computer. I have their panel meter that goes with it. So for me, the data logging is really important. If I had known about the Genasun, I might have gone with it.
But it didn't have the data log.
No. But we'll cover in a minute, you can kind of get around that. The other thing that's really exciting, though, it's like anything else. This guy's $45. That's really cheap for it to be dual chemistry. And I mean, look how small it is. I mean, it's what, a power pole, I think, is 1 inch long, 1 1/4 inches long, 3 inches wide by 1.5 inches tall. That's tiny. That's perfect if you're a field portable, QRP operator. As I'm getting ready to build a new battery box for my Elecraft KX3, I actually have to decide, what do I want to do? Do I want to go with this, or do I want to try one of these Genasuns? Because I'm gonna for that box, I'm gonna go with a 4.6 amp hour lithium iron phosphate pack. So again, it's partly dependent on your budget, partly dependent on what battery chemistry you want to go with. But definitely go with a maximum PowerPoint tracking charge controller if you're trying to squeeze every last ounce of efficiency out of a system. That's the key takeaway. Did I answer your question?
Yes.
Finally, solar panels. The guy on the left is a 7-watt panel sold by Goal Zero, available at Costco in a pack that comes with a 4AA charger that you can charge an iPod or an iPad off of or an iPhone. Both Brittany and I have that in our car for being able to charge a phone if you ever didn't have power and needed to. And also any other USB device. I should have brought it. Yeah.
When it's folded up, it's
And that's the thing, is that guy folds up into a block that's this big, unfolded, it's like this wide.
Okay, just curious.
The array I have in the middle, for those of you who are at field day, that's my 120 watt array that I had at field day. Estimating it's like 36 by like 24 or something. It's not that big. It's yay wide, yay tall on a tripod. And then finally, my buddy whose setup I showed up earlier, these are two 30-watt panels that he got online. And it's about yay wide by yay tall off the ground. So, I mean, considering that that's 60 watts, but those panels are bigger than my 120 watt setup, we'll talk about that here in a second. So, 3 types of panel technology you will consider as a ham. Number 1 is monocrystalline. Monocrystalline solar panels are by forming a giant crystal slowly in an oven and through chemicals and pressure and science and magic and wonderful things. But the point is, the panel is made by cutting a large section of it. So my panels that you saw here in the previous picture, the crystals that are in those were all grown together in one continuous slab. Next, we have the polycrystalline or amorphous. This is made by basically taking a whole bunch of crystal precursors, pouring them into a sheet, and stuff just kind of aligns as it goes, as it happens. They're cheaper, but they're larger for the same output of power, not as efficient in collecting, which we'll go over some of those differences in a minute. Finally, you have thin film. Who has seen at Dayton the power film guys? Yeah?
Yeah.
They have the flexible, look at me, I can fold my solar panel into origami if I wanted to. This technology is useful only for being portable and flexible and a little bit resilient to damage. They are definitely the least efficient of the 3 that we're going to talk about. Panels can be rigid, fixed-framed, aluminum glass, semi-rigid, or rollable/flexible panels. So solar panels are exactly like our batteries, going back to a golden triangle. I can optimize for efficiency and portability, but my cost is going to skyrocket. I can maximize for portability and cost, but my efficiency is going to decline. Or I can maximize for efficiency and cost, but my portability is going to suffer. If we look at the 3 different types of technologies, chemically speaking, max efficiency out of a monocrystalline panel is 20 to 27%, depending on who the OEM is, which sometimes can be hard to tell. Polycrystalline or amorphous drops down to 14 to 20%, and the thin film type panels drop from 12 to 20, depending. It is possible to have a monocrystalline thin film, but they're rare. From a cost perspective, monocrystalline are your most expensive, polycrystalline are your cheapest, and the thin film are in between. From a surface area versus energy, monocrystalline will be the smallest for a given wattage. Polycrystalline will be the largest. Thin film could be anywhere in between. But the other thing is, too, polycrystalline panels are going to be rigid. About the best you'll do is you'll sometimes see suitcase or briefcase solar setups, 2 15-watt panels fold up into something about the size of a briefcase, but they're still going to be rigid. Same thing with polycrystalline, except they're going to be much larger and rigid. Thin film, they could be foldable, meaning that it's a fixed panel, but the thing collapses nicely, rollable, very flexible, etc. One other thing is that as solar panels get warm, they become less efficient, which kind of sucks since they're solar panels. I don't know why they thought, they were thinking about that, but the monocrystalline suffer the least reduction in inefficiency under heating. And when I talk about heating, it's unfortunate. This effect starts kicking in around 80 degrees Fahrenheit. Craig and I have done a few experiments before when I've drug my big panels over to his place. It was air temperature was, say, mid-80s, upper 80s, And just from being aimed in the sun and the fact they're black, the actual panel temperature was about 115. And, you know, at that point, your panels might only get a maximum of 70 or 80% of what they're rated at in the higher temperatures. Now, I just realized I didn't kind of cover this, and I should have put in this chart. What's the lifespan of a solar panel? Does anybody know?
25 to 30 years.
Close. So a good quality monocrystalline can be 20 to 30 years, that is right. However, at that 20 to 30 year period, you're only getting 70 to 80% of its rated energy out of them.
One other question, Jeremy,
Sure.
we're going to get into it. How robust is this monocrystalline panel? If I drop it, is it gone?
So the answer to your question is the monocrystalline itself is incredibly fragile. But these things are built into sturdy welded aluminum frames with thick tempered glass tops on them. All of my panels are monocrystalline. I've only ever dropped one. I dropped it on the asphalt at a height of about 3 foot on the corner. It was fine. I was not fine because these things aren't cheap, but the panel was fine.
Choice words.
Yeah, at least a few. But I mean, the thing is, though, you do bring a good point. Is I mean, you do have to be careful with these things. I mean, all of mine, I have thick padded bags for. I don't let anybody touch them, and it's just because there really is a large investment. And okay, panels going up on your house, the only thing you worry about are tree branches and hailstorms. And if you go into that quality of panel, they're going to be rated for an impact force, you know, on the tempered glass. None of the panels in this level are rated for that because they don't expect you to have to worry about hail and golf balls and whatever else. Sizing. Assume you can get 6 to 8 hours of optimum sunlight. I tell you this because operating solar can sometimes be like operating QRP. The best of intentions does not make your operating day any better. Even though you may get, how long is a day during the longest day in the summer? Like 17?
15 and a half.
Yeah. 6 to 8 hours is a good assumption for your operating, just to keep your expectations realistic. And plus, we'll get into this a little bit, but you also have to make sure you stay perpendicular to the sun. Choose a panel where current times hours of daylight meets or exceeds your battery amp hour rating. So if you're trying to keep your 8 amp hour battery topped off, shoot for at least a 15 watt panel. 15 watt panel is approximately 1 amp at 12 volts times 8 hour charging period. I made this rule up because this has worked for me. I mean, I will admit, I still have a lot more data to collect to refine this. It's also, hey, 1 is none, 2 is 1. Maybe it's better to have 30 watts of panels. I like to carry as many as I possibly can, just because you never know. You may have a completely sunny morning and you may be clouded in the rest of the afternoon. More, you know, I don't remember who said it earlier about doubling your battery. More is always better. It's all about what you're willing to carry and transport. Regardless of what technology you use, solar panels work best when they are directly perpendicular to the rays of the sun. The easiest way to figure this out, for those of you who worked closely with me at Field Day, is to use something that stands perpendicular to the plane of your panels, like a bread twist tie, and make sure to just keep the shadow as small as possible, and you will be tracking the sun. It is possible to build solar tracking frames that either use GPS or, I mean, there are some out there that use differences in heated water in tubes to build a thing that will follow the sun. Portable systems like that really don't exist unless you build it yourself. I'm actually working on one at the moment. And as I pointed out earlier, when cloudy with a good charge controller, it's possible to get another 10 to 25% of your output of your system. Cloudiness is where maximum PowerPoint tracking really pays for itself. Because you may have your panel voltage drop to 10 volts. Other traditional charge controllers won't charge at that level because 10 volts is well below the 14.4 volts that your battery wants, or whatever. Maximum PowerPoint tracking, though, can do the conversion to get it over there. And honestly, most maximum PowerPoint tracking charge controllers are 90 to 99% efficient depending on what current level you're at. Putting it all together, I prefer to work with stuff that's easy, Big fan of Anderson power poles, myself. Quick disconnect, they will keep you from getting your polarities wrong. I highly recommend, in all of my setups, red and black is for anything that goes to a battery or you should be drawing current from. I use gray and green for anything that is a solar panel or should be connected to a solar panel. I also change the orientation so that they're stacked one on top of the other instead of side by side, so you don't inadvertently plug the wrong thing into the wrong place. Current carrying cables, this is true of all ham radio stuff, keep runs as short as possible. Use the largest gauge wire that you can use to minimize resistance. The Goal Zero panels, wonderful form factors. You have a 15 watt panel that comes with the equivalent of a 24 gauge wire, which means I'm lucky to get 9 watts out of it in peak sunlight, just because it has a 6-foot 24 gauge cable on it. I'm in the process of replacing all of the cables on my my Goal Zero panels right now with something that's actually beefy to get max power out of it. Again, yeah, use the largest cables possible to connect. Getting into accessories, meters. Who has a Watts Up? I love Watts Up. Watts Up will tell you your voltage min-max, current min-max, wattage min-max, amp hours. It doesn't log to a computer, but as long as it has power, it will cycle through, and there's even an option to power this thing with a 3-volt supply independent of your battery supply, so it can stay on after you disconnect it. Another new device, I've actually had some input on the most recent version of firmware for this, the Power Check by West Mountain Radio. It's basically a Watts Up with a much more powerful microcontroller inside of it. This thing has gas gauges, like you can tell it, program it to say my battery system gives me 40 amp hours of stuff, and it will give me a gas gauge. It'll flash red and beep when you get to a low voltage point you can set. Most importantly, I can connect this thing to a computer. I can log data out of it. It's serial data over USB. And this thing itself will store, I can't remember if it's 15 or 30 days worth of data in its memory that you can download. It's, again, a Watts Up meter on steroids. Problem is it costs twice as much. The Power Check is about $120. The Watts Up meters are like $50. You can get both of these at HRO. We talked earlier about your batteries when you're home. Sealed lead acid chargers. You want a quality charger to keep your batteries plugged in and maintained, and especially if you're using this for emergency communications, you want to be ready to go. Keep your batteries plugged in at all times. Most importantly, this will extend the life of them. The very popular, what are these things called again? Battery tenders. They come in all different sizes from... Battery Tender Junior, the Battery Tender Plus, which is the one on the right, which is 1 1/4 amp charging current. I have a Battery Tender Marine, which is waterproof and will do up to 5 amps of charging current. They make battery tenders that have 2 charging stations, 4 charging stations, 10 charging stations. They're quality stuff. Well, on the side of lithium chargers, a lot of this technology comes from our friends in the RC hobbies. People like to fly RC planes, drive RC cars. In fact, earlier I talked about you'll have a constant current mode. Saturation mode, they ramp the voltage up for just a little bit. Topping is not like a float charge. A float charge is continuous. Topping is every 5 minutes I check the voltage of the battery. If it's decreased, a millivolt, I zap it. So similar to float, but a little bit different. Lithium chargers, the 2 that I have on the left, they're available through Buddy Pole. They're also available at pretty much every hobby store you go into that has an RC section, by a company called Rev Electrics. The one on the left is interesting. It's $165. It will charge any type of lithium battery with any connector on it, but more importantly, it will do detailed charging of lead acid batteries. Another nice thing is this company, for it's I think a $10 or $15 option, you can get a cable that will let you plug it in via USB and log data out of it. They make bigger chargers also that you can use as basically a programmable DC load if you need that for whatever reason. What it does is if you're trying to measure the discharge rate of a battery, you hook it up to a near empty sealed lead acid battery and it will charge the sealed lead acid battery, but it's basically energy transfer. The one in the middle is specific only to lithium batteries. It will only charge lithium batteries because it only does it through the balancing port. If you don't want to buy one of these, but you still know it's important to balance your lithium cells, on the far right is a little device called a Blinky. A Blinky is a device made by a company called Astroflight, and what it does is you attach it to the balancing lead on a battery pack, and basically just using discharging, LEDs and resistors, and a little voltage divider or whatever, it will keep going until all the LEDs are the same current, same voltage, same brightness, and then it will turn itself off. So it's a passive way of balance. It's balancing through discharging rather than balancing through charging. And it, that thing's like $20. Next on the list, low voltage disconnect. These things are key to keep you from accidentally killing your batteries. Most of them have programmable points where it will disconnect or at least sound an alarm. Buddy Pole has a new one, $40. It's got a little trimmer pot on there that's detented. West Mountain Radio has the PowerGuard Plus. This box is $100 and some odd for $20 worth of function. I don't know why it's so expensive, but you can program a min and a max on it. PowerWorks makes one also. It doesn't have power poles on it, but it's a much higher current thing. Again, just a nice piece of safety gear to have. DC to DC regulators. If you are running an ICOM radio, you might need one of these to get full power. This takes a lower DC voltage, ramps it up to a higher DC voltage. This N8XJK is one of the best ones on the market. It's also about $150 to $200. They come in different amp capacities, 20 up to 80. Some are waterproof, some aren't. The neat thing about this particular unit is you can hook an antenna up to it, and it will detect RF and only kick on when you're transmitting, so it's not using power. This guy is only 85 to 90% efficient. The other thing you got to be careful about this is while it does have a low voltage warning, it's not a true disconnect. You could run a battery dead with this guy and still see your voltage at the radio at 13.8 volts. This thing works incredibly well, zero RFI out of it. It's wonderful. I have recently become aware of a Chinese version of this that's much smaller, a little bit lower current, doesn't have all the bells and whistles, but it's $40. So eBay DC to DC regulator or converter. Moving on to inverters. An inverter takes DC power, 12 volts, kicks it up to 110 volts AC, again through science and magic. Primarily two types. You will hear them called modified sine waves, and if you look at it, it is a filthy square wave. And by filthy square wave, I mean most of them only have 3 points, plus 100 and whatever the peak-to-peak voltages of AC, 130 whatever, 140 whatever, 0 for a period, and then all the way to the bottom. A lot of the modern laptop power supplies.
They don't care.
No, yeah, modern laptop power supplies, USB chargers, your iPhone charger, they really don't care as much. They've got enough stuff going on inside of them that it's fine. The ICOM 92AD, the little wall wart that it comes with, it will not work on a modified sine wave charge inverter, at least none that I've tried it with. No, I take that back. It will. It's the FT60. The ASU FT60 charger will not work on a modified sine wave inverter. It's fine with a pure sine wave one. But if you're going to buy one, the trip lights have the cleanest, lowest distortion energy coming out of them, but it's still a really nasty square wave, or series of stepped square waves.
I think that's the 600 watt version of that's what's in the trailer, by the way.
Yeah, I mean, this little guy right here, you can get him as low as 100 watts. I think the one in the picture there I have is like a 250 or 300.
Well, it's been only recently, it's been expensive to get the pure sine wave.
Oh, it's still pretty expensive.
Yeah.
So what I have in the picture here, a company called Xantrex, Xantrex, and a company called Samlex, which you guys all know Samlex.
Right.
They make pure sine wave inverters that are not huge. Like I have a 600 watt version that's about yay long by yay tall by yay thick. It's got a USB port. It has built-in metering. It was like $220 for a 600 watt version. 1,000 watt version is like 300. 2,000 watt version is 400. Xantrex or the Samlex ones are a little bit more expensive because they'll have some weatherproofing in. I mean, they're built to be installed in commercial marine equipment and stuff. Again, they're expensive. They're not necessary. But one thing I want to point out, because somebody actually suggested I do this once. Build your battery setup, get your solar panels out there, hook your inverter up. Do not plug in your ham radio switching power supply. Do not switch from 12 volts to 110 into your power supply to step back down to 12. I have seen people do this. Actually drag their little Samlex, 1223 out with them, or their Astron or whatever, and not just run the radio off of batteries. Don't do that. You guys are all smarter than that.
Well, the only reason they're doing that is to basically recreate that DC to DC box.
Effectively, but at a cost of like 33% efficiency or more.
I would suggest more like 65%.
So yeah, keep 12 volts at 12 volts. Good thing to have, not necessary. What I want to say is that this can be like ham radio, as expensive or as cheap as you want it. If you are really inspired by this talk today and you're just dying to go out and put a station together to borrow that solar panel, you can go to Harbor Freight down in Woodbridge. They've got a kit that comes with 3 15-watt solar panels that are 3 foot by 1.5 feet. My 15-watt panels are 18 by 11. Okay? But their kit with a 7 amp hour non-intelligent charge controller, how much? They're like $90, something like that.
You mean with the 3 panels?
The 3 panels and the controller.
No, they still run about. The normal price is about $220, and they'll put it on sale around $160, $170, somewhere in that region.
Okay. I mean, at the end of the day, a lot of the stuff ordered online, there is a little bit of money in it. It's like anything else. This is an area, though, where you will receive dividends the more money you put into it. Be it smaller panels, more efficient panels, smaller batteries. But there are a lot of places online you can go and buy panels that are workable size. You could get, Don, just out of curiosity, how much is, say, a 50-watt polycrystalline panel?
That one is around $80.
I mean, comparatively, my 15-watt monocrystalline panels from Gold Zero, if you catch them on sale at Costco, are $89 or $99 a pop. And the thing is, charge controller you can put together for spend $50 to $100 on, depending on what features you need. Your battery is your choice. Most people that start with this are going to run over to Batteries Plus and buy a 20 amp hour battery, a 12 amp, whatever. And you can get started playing. And the nice thing is that charge controller is going to continue to work. Your panel is going to continue to work as long as you take care of this stuff. Your battery might be disposable depending on how rough you are with it, but I encourage people to experiment. Experiment because you want to be able to run a radio when there's no power. Experiment because you want to go sit in the park for 6 hours. It doesn't even have to be complex. For the little 7 amp hour gel cell, you can go buy a 5-watt panel on eBay for $20 and just hook it up and just use it as a trickle charger because it's not dumping enough current into the battery to damage it. In fact, if you buy a Volkswagens are shipped, or the ones that aren't made here or in Mexico, they're shipped overseas with a 3-watt panel suction cup to the windshield to keep a float charge on the battery on the path over, and it just plugs into the cigarette lighter and back feeds into the battery. It doesn't take much. But, I mean, again, experiment. My next, I built my first battery box that's fully functional. My next one is going to fit into a small Pelican case to allow me to run a KX3 indefinitely. And I'm going to start using lithium batteries and maybe play around with some of these small lithium charge controllers.